Good morning to all. This is Vengal Narendra, Assistant Professor of Mathematics. Today we will discuss the topic the numerical methods and complex variables. In the first topic is complex differentiation. We will discuss today about the complex differentiation. Complex differentiation. To understand the complex differentiation, first we have to know what is complex variable. Now already you learned in intermediate level complex variable. Now what is the complex variable? Now suppose x and y are two real numbers. X and y are real numbers. X and y are two real numbers. Now a number of the form, it is denoted by z. Generally z is equal to x plus iy. Z is equal to x plus iy. This is called as a complex variable. Now here z is equal to x plus y is called as a complex variable where x and y are real numbers. Now here, x is called as real part of z. Now you write x always here real part of z, that is REZ. You can write real part of z. Real part of z is here x. Now this real part of z is x here. Next, imaginary part of z, imaginary part of z is equal to y. Now this is imaginary part of z is equal to y here. Okay. Now here, how can you identify? So real part of z. Now x in terms of z. If I would like to write x in terms of z, I need to know complex conjugate. Now suppose if z is x plus iy is a complex number, complex variable, then z bar is equal to x minus iy. X minus iy is called as a complex conjugate. Now here by using these two complex conjugate and complex number, we can write real part of z, that is x you write in terms of z, you can write y in terms of, you can also write in terms of z if you want. Now here from this x is equal to z plus z bar by 2 and y is equal to z minus z bar by 2i. Now in terms of z, if I need x in terms of z, using this principle, just add it here, z bar, you get 2x, that is x is equal to z plus z bar by 2. If you subtract it, z minus z bar, okay, now iy plus iy, 2iy, you get z minus z bar is equal to, that is y is equal to z minus z bar by 2i. Next, sometimes we need to identify, we need to write the complex variable in terms of polar form. Now how can you write the polar form? Now here, now if you put x is equal to r cos theta, x is equal to r cos theta and y is equal to r sin theta. If you write y is equal to, put y is equal to r sin theta, then z you can write r into, z you can write r into cos theta plus I sin theta, that is cos theta plus I sin theta can be written as e power I theta. Now this is the polar form of the complex number z is equal to r e power I theta. Now if you need in terms of polar form, a complex variable in terms of polar form, if you need to write, we can use this form, that is z is equal to r into e power I theta. This is now here, to understand the differentiability, we need to know one more definition, that is neighborhood of a complex number. Neighborhood of a complex number. Neighborhood of a complex number. Now which one we called as a neighborhood of a complex number? Suppose the set, you can take the set z is equal to the set you can write, that is z minus z naught, modulus of z minus z naught less than epsilon, where epsilon is greater than 0. You can take the set, that is z minus z naught less than epsilon. Epsilon is always a positive number, that is greater than 0, just greater than 0. This is called as a neighborhood of a complex number z naught. Now how can you represent here? Suppose any z naught is here, any point is there in the complex plane, any point is there, the neighborhood of this complex number you can write. This is the form of, that is just you take that one, very small here, the radius is epsilon greater than 0, just you take the epsilon greater than 0. Now this is called as a neighborhood of a complex number. Now this is neighborhood of a complex number. Now any complex number if you can take, that is the, now the region what here I denoted here the dotted lines, that complete considered as a neighborhood of a complex number. Okay, any point if you take any complex point you can take, the neighborhood you can take in the form of circle form. A disk, you can take the disk here, called as a disk. The disk, this is the disk is called as a neighborhood of a complex neighborhood of a complex number. The number if you denoted here Z0. Is it clear? Now here, suppose here if you deleted neighborhood of a complex number, we can also use another term, deleted neighborhood of a complex number. What is here deleted? 0 less than Z minus Z0 less than epsilon, modulus of Z minus Z0. Okay, this is called as a deleted neighborhood of a complex number. Now here the point does not there here, that is here you can take. Okay, now here if you remove this one, the remaining part you consider, the point does not consider that one. Okay, that is called as a deleted neighborhood of a complex number, deleted neighborhood of a complex number. Okay, now here, now what is the function of a complex variable? Now here we learn, okay, neighborhood of a complex number, what is complex variable, and polar form of a complex variable. Now here, what is the function of a complex variable? Now you see function of a complex variable. Function of a complex variable. Now how can you define function? Already you know in real theory what is a function, you know that. The same way here you can define here on the complex numbers, and the complex variable we define function. For every complex variable z is equal to x plus iy, there corresponding to the another complex variable, that is w is equal to u plus iv. W is equal to u plus iv. For every complex variable z is equal corresponding to another one or more variables, you can add one more term, that is one or more variables, w is equal to u plus iv, then w is called as a complex function, that is called, you can write w is called as a complex function, that is w is equal to f of z is equal to, that is you can write u of x comma y plus I into v of x comma y. Now w is equal to f of z is equal to u of x comma y plus I into v of x comma y. Now this is a function of, that is complex function, you call it as complex function f of z. W is equal to f of z. Here w is the complex function of the function complex variable z. W is equal to f of z. Now here one or more variables. Now here if you are there, for every z there is only one variable w, then it is called as a single valued function. Single valued function. That means for one value you have only one. Now for wz, that is otherwise you call it as multi-valued function. Now here multi-valued function and single valued function, depending on the function values we decide that is a single valued function, the given function is a single valued function or multi-valued function. That's why in the standard definition one or more variables, corresponding to one or more variables, we add that one. If it is one, we call it as a single valued function. If it is more than one, we call it as a multi-valued function. Example, you know very well, that is w is equal 1 by z. This is one example of single valued function of a complex number. Now here w is equal, if you take log z is a multi-valued function, complex function. Okay, multi-valued function. These are some examples to understand what is the functions of a complex variable. Okay, next, what is the limit of the function? Now here you know in real theory, you know limit of a function, you know that. Similarly we can define limit of a complex number. Now limit of a function of a complex value, limit of a function f of z at a point I suppose that is z0, limit of a function f of z at a point z is equal to z0. Now how can you define limit of a function at a point z is equal to? Now this is similar to the real theory, but there we can consider the real numbers only. Here we consider that is a complex numbers only, that is the difference. Now the definition almost similar, wherever you take the real number, just you take the complex number here. Now for the classical definition, how can you define? Okay, for every small real epsilon greater than 0, there exists a real there exists a complex number delta greater than 0 such that modulus modulus of f of z minus L less than epsilon, modulus of f of z minus L less than epsilon, whenever modulus of z minus z naught, modulus of z minus z naught less than delta, modulus of z minus z naught less than delta, then this complex number L, is called as a limit of a function f of z at a point z is equal to z naught. Symbolically, it is denoted by limit z tends to z naught f of z is equal to complex number L. That is limit z tends to z naught f of z is equal L. Symbolically we denote this one. This is a limit of a function at a point, limit of a function f of z at a point z is equal to z naught. If you get that L may be real, no problem, real or complex, because it is a complex. Real is nothing but the subset of complex, you know that, therefore L may be real or complex. Now this L is called as a limit of a function f of z at a point z is equal to z naught. After understanding the limit definition, we can define continuity of a complex function. Continuity, how can you define the continuity? Continuity of f of z at a point. Here also we can define at a point, at a particular point we can define first. At a point z is equal to z naught. Now here continuity of a function f of z at a point z is equal to z naught. Now how can you define the definition? Whatever you learn in the real theory, the same here, but here there we consider the real numbers in the real theory, here we consider the complex numbers. That is the difference. Here always you in the complex, always you can take z is a complex number only. Of course though it is a 2 is also considered as a complex number. Okay, 2 plus I into 0. That means there 2 considered a complex number means the imaginary part is 0 in that case. You think in that manner, you can understand the concept. Now the continuity of a function f of z at a point z is equal to z naught. Now how can you define the same definition? The limit here we can add the function value at the point, at that point. We can add the function value at that point. What you did, function value at that point f of z naught, it is exists. Now here f of z naught exists. The function value at that point exists. If it is equal to the limit value, you can say that is continuity of a function. Okay, if it is not equal, you can say that is discontinuous. It is not continuous. You can, so you know that the same here. Now how can you define the definition here? For every small epsilon greater than 0, there exists a delta greater than 0 such that modulus of f of z minus f of z naught less than epsilon whenever modulus of z minus z naught less than delta. Now here this is the that means function approaches to function value. Function approaches to function value. Here z approaches to z naught. Now z approaches to z naught very small, very small. Then the function approaches to function value, that is also almost near to equal. That means almost near to equal. Symbolically it is denoted by limit z tends to z naught f of z is equal to f of z naught. Limit z tends to z naught f of z is equal to z naught. This is the continuity. If this condition satisfies, here f z naught exists, f of z naught exists and equal to the limit value, you can say the function is continuous at a point z is equal to z naught. Symbolically we write this one, limit z tends to z naught f of z is equal to f of z naught. Now here if the function is continuous in the region R, suppose if any region, if you take any region, the function is continuous at each and every point, continuous at each and every point, then you can say the function is continuous in that region R. Now here we have to check a function f of z is said to be continuous in a region R if it is continuous at every point of the R. At every point, if you can take any point in the region, at that point the function should be continuous. Then you can say the function is continuous in the region R. Now here next after continuity you try to next you know that what is that differentiability. Extension continuity is nothing but differentiability. What is differentiability of a function in complex variable? Same thing here, you can the definition also be there. What is the difference here? We always consider here complex numbers, there we consider in the real theory we consider the real numbers only. Now differentiability of f of z, here also you can take at a particular point z is equal to z naught. differentiability of f of z at a point z is equal to z naught. Now here, how can you define differentiability? Now the derivative of function f of z, the derivative of f of z at a point z is equal to z naught, the derivative of f of z at a point z is equal to z naught is denoted by f dash of z naught. Now this is the notation of derivative, you know that, f dash of z naught, and is defined as f dash of z naught is equal to limit z tends to z naught, f of z minus f of z naught, divided by z minus z naught, exists. If it exists, you can say the derivative exists. Okay, now this is, if it exists, you can say that is the function is derivable. The function is derivable at a point z is equal to z naught. Okay, the derivative of the function f of z at a point z is equal to z naught is denoted by f dash of z naught and is defined as f dash of z naught is equal to limit z tends to z naught, f of z minus f of z naught by z minus z naught. If it exists, you can say the function is differentiable at a point z is equal to z naught. Symbolically we write this one, f dash of z naught is equal to limit z tends to z naught, f of z minus f of z naught by z minus z naught. Now here, this is the differentiability of a complex function f of z at a point z is equal to z naught. Now here, now how approaches here, always we consider the limit of a function or continuity or differentiability. How approaches here? Now here in the real theory, now compare here the real and complex thing. Now how approaches here? Now how approaches here? We observe here in the real theory, how the limit approaches here. If you are taking any x here, x naught, you have taking x naught. Now here x approaches to x, here x approaches to either from left side or from right side. X approaches to either from left side or from right side in the real theory. Now here the limit concept. Now how you consider in the complex? Now here infinite number of ways. Now the z approaches to z naught in infinite number of ways. Now any complex function, complex variable, here is x real part, here imaginary part, this is I, imaginary part, here real part, imaginary part. If you are taking, now any point is taken. Now here, now any point, if you take any point here, suppose any point you are taking, now z naught I am taking, suppose z naught I am taking. Now how you approaches the z? Here infinite number of ways. In the real theory only either from left side or from right side. X approaches to x naught. Only two ways only possible in the real theory. In the complex you can hear infinite number of ways. Now z here moving. Now here z is there. Now here z approaches to z naught. Here z naught is there. Z approaches to z naught in infinite number of ways. You can in any direction. There is no specific direction here. Here infinite number of ways z approaches to z naught. Here z approaches to z naught in infinite number of ways. Now always you take the neighborhood. Here always you can take the neighborhood, and here you consider z tends to z naught. Z approaches to z naught. Here in this way we get, here we can consider infinite number of ways. Now if it approaches to z naught in infinite number any way, you observe that is satisfied the same value, z approaches to z naught. Okay, then only you can say limit exists. Similarly continuity, similarly differentiability. Now here differentiability, z tends to z naught. Now the ratio of difference between f of z minus f of z naught by z minus z naught. That is you consider, you know the very well. Definitely in the real theory here compared with the complex theory only. Now here, that is the approaching way. Now here limit approaches to x tends to x naught and x either from left side or right side, that is in the real theory. And then the complex theory, z approaches to z naught in infinite number of ways. Now in any direction it approaches to z naught. Now that is the only the difference. If you understand this concept, okay, you can enjoy the concept each and everything. What is how approaches z tends to z naught? You can take any number of ways, not only the straight line. Okay, the curved line also you consider. Whether it approaches to z naught along the curved line or along the straight line, whatever the path you can take, all paths you consider. There is no restriction. All paths you consider. If it exists, you can say that is limit exists. Otherwise, if any path is there, in that path the value does not exist, or the value is not equal to the other path, we can say limit does not exist. Thank you.